Welcome to the next part of Lecture 1. We're looking at portion 2 today, and we're focusing on the nature of soils as can be seen in Craig 1.2. The rock weathers into soil as follows. Firstly, in physical weathering, we have erosion by the action of wind, water, glaciers, or disintegration caused by cycles of freezing and thawing in the cracks in the rocks. The soil particles retain their mineralogical composition in physical weathering, and the particle sizes can vary from boulders to sand and fine rock powder. Each particle in direct contact with adjoining particles with no binding. So you have a single grain structure as can be seen on page 7. And the relative density can be loose, medium dense, dense, and very dense. When the rocks are broken down, on the right top you see the angular materials, typically like your hill wash you find on the sides of mountains. Then as they roll down the mountain, they become subangular. Then as they are moved, typically by water, you start getting a sub-rounded nature, then rounded, and eventually very round, which is almost spherical. So this is the physical weathering products. Then the other form of weathering, of course, is chemical weathering, where you have a change in the mineral form of the parent rock due to the action of water, oxygen, and carbon dioxide. The clay minerals or clay particles is in the size of less than 0.002 millimeters, and on the right hand side you see a SEM picture, a scanning electron microscope picture of typical clay particles. We're going to focus a lot on clay particles because it influences the nature of soil the most, and we will deal with that for the rest of this module. Clay particles are typically in a plate-like form, so they have a high surface area to mass ratio. And they have some basic structural units. First of all, the silicon-oxygen tetrahedron. Then there's an aluminium hydroxyl octahedron. Those are your two typical structural units of clay. And then valency imbalances causes net negative charges on these clay particles. And so these structural units combine to form sheet-like structures. So this is a silica sheet at the top, which is basically a combined set of tetrahedrons, and a gibbsite sheet is a combined set of octahedrons. Those are the basic clay particle units. If you have a silica sheet, it has a net negative charge, whereas gibbsite sheet is neutral. So what happens if you have isomorphous substitution is when the silicon and aluminium is partially replaced by other elements which further change the imbalance. The layer structures formed by bonding of a gibbsite sheet with one or two silica sheets. And there's a picture in the handbook, and I will show it a little bit later as well. So clay minerals or clay mineral particles consist of these stacks of these layers. One gibbsite sheet with one or two silica sheets. There are different forms of bonding in the clay particles. The surfaces of the clay mineral particles carry residual negative charges, mostly due to the isomorphous substitution of silicon or aluminium by ions of lower valency. So the surface carries a residual negative charge mostly. The cations in the pore water around the clay particles are attracted to negatively charged clay particles. The cations are not held very strongly, so if the nature of the water changes, it can be replaced by other cations, and this is called a base exchange. And then thermal energy causes cations to move away from the clay minerals. So the cations form a dispersed layer adjacent to the particle. We'll see a picture just now. And if you have a double layer, so you have negatively charged particle surface and a dispersed layer of cations. And layers of water molecules are also held around the clay mineral by hydrogen bonding and an attraction to negatively charged surfaces. So if you look at this picture, you have the negative charge on the clay particle itself, and then the dispersed layer of cations and anions adjacent to the clay particle, and the cations are more than the anions. And also the pore water is attracted to the clay material, and you have this adsorbed layer of water around the clay minerals. These are the three main types of clay that we get, and we've seen this in engineering geology, but let's look at it again. The kaolinite on the left-hand side, one gibbsite layer and one silica sheet held together by hydrogen bonds. Then the illite is one sheet gibbsite with two sheets silica on both sides, and they have a potassium ion bonding which is relatively weak. And montmorillonite, again, one sheet gibbsite and two sheets silica, but held together by water. So kaolinite is very strongly bonded, so kaolinite clay is inactive. It's typically white or pinkish, but not active. Weathering product from granite typically. The illite is medium active, typically gray, and then montmorillonite can have different colors, but this is the most active clay that we get. This is the one that causes heave and damage to buildings. So kaolinite, as mentioned, is one silica sheet and one gibbsite sheet, and it's strong hydrogen bonding. Illite is one sheet gibbsite and two sheets silica, and it has a relatively weak potassium bonding, and you have now partial substitution of silica with aluminium. Montmorillonite, again, one sheet gibbsite and two sheets silica, but it's water molecules and exchangeable cations that forms the bonding, so it's very weak and it can therefore expand. And also with montmorillonite, you have partial substitution of aluminium with magnesium and iron, and silica with aluminium. Then you have forces of repulsion and attraction between adjacent clay minerals. The net inner particle forces influence the structural form of the clay. So if you have net repulsion, you have face-to-face orientation. This is known as a dispersed structure. So the flat parts of the sheets are combined or attracted to each other. If you, however, have net attraction, then you have either face-to-edge or edge-to-edge attraction, and this is known as flocculation. So again, face-to-face or edge-to-edge or face-to-edge attraction. So this is typically the flocculated and dispersed structure that you get from clay minerals. Clay minerals exert a considerable influence on the properties of a soil. So that's why we will focus a lot on the clay and the activity of clay in the future lectures of how it influences man's structure. If you have a fine-grained soil, the properties are mostly influenced by the clay and silt particles, whereas if you have a coarse-grained soil like a sand, the properties are more influenced by the sand and gravel. So your coarse-grained soils typically will not have heaving potential, but it may have a collapse potential or compressible nature. This is the end of portion 2 of lecture 1. Thank you.